Hey, it's too bad you're not here because this is actually one of my favorite AP discussions to have, at least my favorite acid-based thing. So this video, whether you're coming back to it later and you're in class or whether you're at home, is going to have a lot of key conceptual things that help you define and understand strong and weak, that help with titrations, that help a little bit with introduce the idea of buffering and answer a lot of the conceptual things that go along with acids and bases. So I'm going to do my best to keep all the energy up and to get the information to you in an easy to understand way. But know that you'll still have some questions at the end of this. It's going to take some practice and asking some questions. So the two things we're going to look at are titration graphs. It's both for a titration of an acid with a base. The one we'll do first is a strong acid, and specifically, as it says, HCl. So we're going to do a couple different things with each of these. There's no question specifically here, just a titration curve, some beakers, and some drawings. And our goal is to kind of get through just a whole bunch of kind of everything we know about this scenario and try to put that all in one place or on this one page. So the first thing we want to think about is writing that as a net ionic equation. So HCl with NaOH makes water and NaCl. We should know that strong acids and strong bases completely dissociate. We should also know a limited number of solubility rules. For example, that sodium compounds are always soluble. So when we think about this as a complete ionic, the things, forgot my pen there. The things floating around are hydrogen ion and chloride ion. It's not HCl. It is sodium ion and hydroxide ion, not sodium hydroxide together. It is sodium ion and chloride ion because that's soluble, but water is a covalent compound. It is polar, but it's only partially soluble. So if that's our complete ionic, chloride and sodium appear as ions on both sides. So we really want to clean this up and simplify it down to hydrogen ion plus hydroxide ion makes H2O. Some things we know about that is that goes mostly or pretty much all the way to completion. Hopefully we recognize that as the opposite of water breaking into its ions. So H2O breaking down into H plus and OH minus is the KW reaction in the KW equation. That has a KW 1 times 10 to the negative 14th, which means that when I do the reverse reaction of that, this reaction, it has a really big K, 1 times 10 to the positive 14th. So not just talking about millions or billions, we're talking about hundreds of trillions in terms of our value of K, and it's really big and it goes to completion. So whether we're talking about these specific strong and acids and bases or any strong acids and bases, that is the net ionic equation, and that huge value for K is the evidence that it's going to be a one-way process. As we look at our titration curve here, we can observe a few things. The pH starts low, it stays low for a little while, rapid increase and ends high, which tells us what's in the burette and what's in the beaker. So the burette up here, our beaker or our flask down here, because the pH starts low, that is our acid, and up there is our base. The acid is really low, and if I knew the exact pH, because this is strong, I could know the molarity of this HCl. So then what we're going to do is draw what ions would we see in the beakers at all of these different points if I started with HCl here, started with NaOH there, and went through this reaction, knowing that it's a one-way reaction and knowing that the hydrogen and hydroxide are forming water. So initially in our beaker, that is when we've added 0 milliliters of base. So we only have HCl. But in doing that, we want to think about, well, what would the HCl look like? We wrote it as a net or complete ionic. So when we put HCl's in here, they're not HCl. It is H ions and Cl ions. H ions and Cl ions. H ion and Cl ion. So I can also simplify that, and this makes it a little bit cleaner as we go through this and the next video. We're just going to put a small number so we don't go crazy, but a number of ions there, and recognize at the beginning we have no HCl molecules. We have a certain number of hydrogen ions, and those hydrogen ions are equal to the number of chloride ions completely dissociated. The negative log of H plus tells us our pH. Since we have our pH, 10 to the negative pH could give us our H plus molarity. We have added no base, but as soon as we drip from 1 to 2 to 3 to 4 and then end at 5, we're going to be adding to it a certain number of bases. So we think here this had 4 HCl's. We've got beaker 2, beaker 3, and we're actually going to jump ahead to the next most important place in a strong titration, or really any titration, the equivalence point. The equivalence point is when moles of one reactant is stoichiometrically equivalent to moles of the other. For acids and bases, we often say moles of acid equals moles of base. Or another way to think about it that's important to recognize is it's when our hydrochloric acid, or in this case, our acid, goes from being the excess reactant to being the limiting reactant. So those are 3 different ways of recognizing or defining our equivalence point. So if my beaker started with 4 HCl's in it, to get to the equivalence point, based upon our 1-to-1 ratio, we will need to have added 4, kind of sloppy there, NaOH molecules. These two may have the same molarity, so it may be a certain number of milliliters of this and an equal number of milliliters of that. Or most often, we are given the volume of HCl that's in our beaker. We measure the volume of our base from our burette. We record the volume, dropping that point down, of base. And by knowing the volume, if we're doing a titration, we look at that volume, or we could look at this, getting a little confused there. We use that volume and we know the molarity of it. Lost my train of thought there, but hopefully you understand the idea. By reading our burette, we see at what point did we get that big peak, or our equivalence point, or did we have the steepest, or in terms of calculus, have an inflection point. But right here, this is what we're thinking about. Well, what would be in the beaker? It's not 4 hydrogen chlorides or HCl's and 4 NaOH's, because we've added enough of each reactant that they reacted. We have gone from reactants and we are making products as we go. So our products we defined as H2O and NaCl. So if I'm right here in my beaker, I will have added enough hydrogen ion and enough hydroxide ion to make water. And with 4 of each, if that's what I'm thinking about here, there would be 4 waters right there. I would also make 4 NaCl's, but that NaCl is not floating around as bonded together NaCl. If it were a solid that was insoluble, it would be, but because sodium is soluble in all cases, we would have 4 sodium ions and 4 chloride ions floating around in there. That we have a certain volume, and we see, because it's strong with strong, our pH is 7. Water is neutral, and sodium, because it comes from a strong base, chloride, because it comes from a strong acid, is totally neutral as well. So that's probably the most important place. You might get some questions about your initial pH. Do some stuff with K, pH, etc. Do some stuff with molarity there. 2, 3, and 5 are when we don't have an equivalent amount. So in 2 and 3, you want to think about, we are doing the reaction, but we still have limiting excess. 5, we're still doing the reaction, but we're thinking about limiting excess. So let's jump up to 5 here. Based upon the pH, based upon the curve, based upon what we've already seen, up there, the excess would now be the sodium hydroxide. It's not super clear exactly where 5's pointing to, but if I had something like 4 HCl, it might take like 6 NaOH's to get that far. Maybe you would think 5 or 7 or 8. All of those are fine answers. It's just that there's more of this than this. If I have those, what have I made, or what is actually in the solution? Well, I still have 4 H's and 4 OH's, so I can make 4 H2O's. But there's 2 OH's that don't have a hydrogen to react with them. So I have 2 hydroxide ions in excess. Those 2 hydroxide ions come along with some sodium ions. And we might be tempted to say we have 2 sodium hydroxides, but we don't. We have 6 sodiums floating around. So this would also be in the beaker, even though I ran out of space. So there's 6 sodiums in there, but those 2 charges do not equal each other. Our charge within a beaker, one of the tricks, if you see this in multiple choice, or if you have to draw it in free response, is that the number of cations and anions with their charge and number, they have to be equal and opposite. We've got too much positive charge because we haven't yet accounted for the fact that we still have 4 chloride ions. We started with 4 chloride ions. At the equivalence point, we had 4 chloride ions. After the equivalence point, we still have 4 chloride ions. And we'll see in beaker 2 and 3, the same thing. When you have a certain number of moles of your strong, in this case, HCl, that anion stays the same all throughout the titration, before and after the equivalence point. So that's a spectator that stays the same in its amount. When I come down to beaker 2 here, an important thing to note is that's about halfway to the equivalence point. With weak acids, that's a super important point. And with strong acids, it's a little bit less important, but it does allow us to think about changes in pH, changes in reactants and products, and changes in concentration. So if I have 4 HCl's, that used to be 4 H's floating around. And if we think about, well, I had 4 H's and 4 Cl's, well, now I put in 2 NA's and 2 OH's. The problem is H and OH combine. So we don't have any OH's right here. We have an H that has reacted with both of those OH's. So we've been able to make 2 water molecules. We have added in 2 sodium ions. We have, as we said before, 4 chlorides that stay in solution. But probably the most important ion here is the fact that we have in there 2 hydrogen ions. So the pH is still low. This solution is still acidic because I still have hydrogen ions in solution. As we look at the pH change, we see, well, I have half as much pH, but it only, or H plus, but it only nudged up a little bit. Remember, to change a whole unit of pH, we have to change the hydrogen ion concentration by a factor of 10. So to go from here to here, we haven't changed our hydrogen ion concentration by a factor of 10. We've only cut it in half. So our pH has changed by less than 1. We still have some hydrogen ion. Our chloride ion has stayed the same throughout. We have a little bit more sodium ion in there, and we have made some water. The next one, also not super important other than practicing our stoichiometry and setting the framework here, but hopefully you could predict pretty accurately that that would make 3 waters with 3 sodiums, still 4 chlorides, and only 1 hydrogen left over. One thing to note, if you had to do math here, here, about maybe the molarity of the chloride or the sodium, an important piece, yes, the moles of chloride stays the same, but throughout, remember, we're mixing 2 liquids together. So our volume is actually increasing. We have whatever volume of hydrochloric acid we had. We have whatever volume of sodium hydroxide we have added. That's our new total volume. So the moles of chloride never changes, but the molarity does go down a little bit. The molarity of hydrogen ion goes down a lot until we have excess hydroxide, and the molarity of the sodium ion increases as we go. So those are most of the key ideas of our strong with strong. Setting the framework, thinking about what's in there, thinking of it as a one-way net ionic equation. And no matter what strong acid or strong base we have, we'll use these same basic ideas.